Good evening, everyone. At this point, I'll be your demonstrator teacher for about 20 minutes. Allow me to present to you my crafted lesson plan in physics for grade 10. My discussion will revolve around the magnetic field and the magnetic force. By the way, I am Allan Sumandal, a secondary school teacher in the school's division of Palawan. At this juncture, I'll be showing to you the subject matter and the parts of my lesson blueprint. First is the subject matter. So the topic is about the magnetic field and the magnetic force. The materials to be used all throughout the lesson are as follows: magnets, iron filings, and some visual aids for activities and discussion. In this case, I'm using the PowerPoint presentation. This lesson plan follows the experiential in inquiry approach. As a science teacher, I believe and I advocate experiential theory or learning by doing because I see, based on my own experience, that learners learn best through experiences. That is why every time I start my class, I make sure that there are activities that will elicit their interest and motivate them to participate and learn before I dive into the main topic of the lesson. I also use of inquiry approach to make sure that they learn from their own experiences and they will learn while working with their classmates. This lesson plan that I have created is good for 85 minutes. Now what you can see in your screen is a diagram that shows the flow of the lesson. At the start of the class, I'll be presenting the learning objectives and I will let the students read these objectives loud. After presenting the objectives, there will be two activities related to the lesson for the motivation part. The second part will be about the introduction of the topic. In this part, I incorporated literature like the story of the Mountain of Lodestone, which shipwrecked Sinbad, the sailor of the Arabian Nights. There is also a group activity for the unlocking of difficult terms which the students will encounter during the discussion. The third part is the teaching or discussion process. Here, the concepts about magnetic field and the magnetic force will be discussed. Since this lesson is abstract and there are mathematical computations, I find it practical to have a lecture in this part, then followed by a group activity. The fourth part is the practice session, where students are asked to answer word problems and some situations. The fifth part is about the generalization or the summary of the lesson. In this part, there will be activity, group activity that shows the concepts that they need to ponder and to remember. And the sixth part is the application, and this is where the students share their thoughts, their insights on the relation of these concepts to their daily life and how magnets affects their lives. And the last part of the lesson is the assessment. This is a paper and pencil test type that will measure how much learning they have gained from the whole discussion, from the whole duration of the discussion. This is also the time where I evaluate myself if I have attained the objective. Now at this point, please bear with me as I demonstrate to you some of the parts of my lesson plan. Good evening, class. This evening, we have a new topic which has a great connection to our daily lives. This lesson is also a continuation of your physics lesson in grade 9. So this evening, we will be going to talk about magnets. Okay? On your screen are our learning objectives for this lesson. Can you please read, class, the objectives? Okay, our first objective is you have to illustrate the lines of the magnetic field. So expect that you are going to draw, you are going to illustrate. Number 2, describe the magnetic field and the lines of the field. Okay? Number 3, you have to calculate the magnetic force and the magnetic field of the object. Number 4 is that you have to identify the direction of the magnetic force. And number 5, you have to enumerate home materials that have application of magnets. Now, what you can see in your screen is a bar of magnet and an animated line that show the magnetic field or lines of the magnet. So those blue lines, closed loop lines, are what we call magnetic field or lines of the magnet. This is the same idea what physicists believe that a magnet is surrounded by a magnetic field. We say, and we defined last time from the introduction part of our discussion, that a magnetic field is a region of space, remember of that? Is a region of space where a magnet is capable of exerting a force on a magnetic material. Okay? Or in other definition, magnetic field refers to the region surrounding a magnet in which the force of the magnet can be experienced. That is why if we are going to place a magnetic material near the magnet, it will definitely be attracted because of the force that the magnet exerted. In addition, the number of lines that passes through a surface or plane is what we call magnetic flux. For example, we're going to place a plane or a surface near to the magnet. Uh, this magnetic field or lines of magnetic field will pass through those planes or surfaces. Now, the number of lines that pass through that the surface or plane is referred to as magnetic flux. Now, the more magnetic field lines pass through a surface or plane, the higher the magnetic flux. Okay. Now, in this slide, I know you are all familiar with compass. Okay. Everybody know what a compass is and what it looks like. Well, the compass is a great tool in identifying the magnitude and the direction of the magnetic field. Now, the direction of the magnetic field is the direction in which the needle compass points when in the field. For example, if we put a compass near the magnet, its needle will move pointing to the direction of the field. For example, the needle of the compass points to the north. That means that the magnetic field's direction is also north. Okay? On the other hand, the magnitude of the magnetic field or the strength of the magnetic field is determined by measuring the torque. Okay, remember of that, no? The magnitude of the magnetic field is determined by measuring the torque exerted on the compass needle in the field. No, the movement, the rotation of the needle of the compass. Okay, that means the torque of the compass. That is how we are going to identify the magnitude of the magnetic field. Now, torque refers to the strength of the rotation of the needle of the compass. The greater the torque, the greater the magnetic field. So again, the direction and the strength of the magnetic field can be identified using the compass. Okay? The direction of the magnetic fields depends on the direction where the compass needle points, while the strength of the rotation of the needle compass uh, refers also to the torque, will give us the idea on how to measure the strength or the magnitude of the magnetic field. Now, at this time, I want you to focus on the following facts related to torque and magnetic field. Now, the first um, the first fact about magnetic field and the torque. Number one, torque is the effectiveness of the force in rotating body like the hinge of the door. In our case, the rotation of the needle the needle of the compass. Number two, the greater the torque, the greater is the magnitude of the field. Number three, the unit for magnitude of the field is Tesla, named after Nikola Tesla, a great scientist. Then number four, the Earth magnetic field is about 5 times 10 raised to negative 5 Tesla. Now, there are some word problems wherein magnetic field the number of magnetic field or the measurement of the magnetic field is not indicated. So we'll always remember that the Earth's magnetic field is equivalent to 5 times 10 raised to negative 5 Tesla. And last, the magnetic field is very strong near the poles of the magnetic or of the magnet, where lines of flux are more closely spaced. Okay, so this is true when we conducted the activity in motivation part. As you can see, most of the iron filings are concentrated near the poles. That means there is a very strong magnetic field near the poles of the magnets. Now, at this in this illustration, I want you to describe the lines, no, these lines. Can you describe the lines that surround the magnet? How can you describe the lines that surround the magnet? Yes, correct. Number one, it never cross. Yeah, so you can see it never cross with other lines. It has own path. Okay. Number two, it is continuous. It is continuous. Okay, number three, it formed individual closed loops around the magnet. Number four, have definite direction from north to south pole. Number five, it indicate a strong magnetic field when close together. That is why when we are going to if we put a nail or any magnetic material near the magnet, it will attract it because it experiences great force. While it indicates a weak magnetic field when farther apart, that means if we place an iron or any magnetic material far from the magnet, it will not be attracted because there is a weak force. Next, uh, our next discussion will dwell on the magnetic force. Okay, we know that electric charges exert electrostatic forces of attraction and repulsion on each other while they are at rest. When the charges are in motion, they still exert electrostatic forces along with magnetic forces. Now, these magnetic forces also attract and repels when two lines of force are brought close together. The interaction between the two magnetic fields causes one of these two things occur: attraction and repulsion process. That is why if two magnets, let's say the same orientation, north and north, these two magnets will not attract each other. While if the orientation are opposite, the two magnets will be attracted with each other. This means that north and south poles attract each other, while the north and north poles, south and south poles repel each other. Okay. Now, we defined last time magnetic force on a moving particle. If an electric charge moves with a velocity through a magnetic field, a magnetic force is exerted on the charge. Mathematically, the magnitude of the force and the magnetic field induction are defined as Fm, or magnetic force, is equivalent to QVB sine theta. And for magnetic field, B is equal to Fm divided by QV sine theta, whereas Fm refers to magnetic force, Q refers to electric charge, B refers to magnetic field, and V refers to velocity. Take note of the unit. When we are calculating or looking for magnetic force, our unit is Newton, and if we are looking for magnetic field, the unit is Tesla. Now, let's try this problem. An aircraft whose wingspan is 16 meters carries a static charge of 0.75 coulomb. It travels at 235 meters per second perpendicular to a 1.9 times 10 raised to negative 4 Tesla magnetic field. What magnetic force does an aircraft experience? Or we're given the data. Q is equal to 0.75 coulomb. The V velocity is equal to 235 meters per second. Our B, or magnetic field, is equivalent to 1.9 times 10 raised to negative 4, and our angle is 90 degrees. Now, let's just substitute this given data to the formula. Fm is equal to QVB sine theta. We have to use scientific calculator to get the magnetic force. So overall, our computed magnetic force is equal to 0.033 Newton. Another problem: a proton is traveling 2.4 times 10 raised to positive 6 meters per second in a circular path with a magnetic force of 3.2 times 10 raised to negative 13 Newton. What is the magnitude of the magnetic field on the proton? So again, we're given the value Q, or the charge of proton is equal to 1.6 times 10 raised to negative 19 coulomb. Our velocity is 2.4 times 10 raised to positive 6 meters per second. Our magnetic force is equal to 3.2 times 10 raised to negative 13 Newton. And our angle is 90 degree. So our formula for magnetic field induction is equal to B is equal to Fm divided by QV sine theta. So substitute those values to the given formula. Our computed magnetic field induction is 0.83 Tesla. Now, at this point, we will learn how to identify the direction of the magnetic force. Okay? To find the direction of the magnetic force, physicists develop a rule called the right-hand rule. Okay? Imagine that your right hand is what is depicted on the illustration. Okay? So it states that the magnetic force is perpendicular to both V and B. Okay? Magnetic force is always perpendicular to both V and B. On the illustration, as you can see, arrow B or boy is the direction of the magnetic field. Arrow V refers to the direction of the velocity, and arrow F is the direction of the magnetic force. Meaning, your thumb points the direction of the velocity, yung thumb natin. Your fingers point the direction of the magnetic field, and your palm points the direction of the magnetic force. Okay, if you're going to look for magnetic force, just look at your thumb. What is the direction of the magnetic force? By looking at your uh, at your palm. Okay. In three-dimensional illustration, you will see this. In reality, particles are moving at 3 dimensions. So we have x-axis, y-axis, and z-axis. If the velocity is going to north or positive y-axis, then we have the magnetic field going west or negative x-axis. Then the magnetic force is going to positive z-axis. Okay? So for example, just look at your right hand. Now, remember that your velocity, that your thumb refers to your velocity. If the velocity is going to north, meaning positive y-axis, then your magnetic field is going to west, or the direction of your fingers. So, meaning negative x-axis. Then your palm, which is the direction of your magnetic force, is going to positive z-axis. That's how are we going to identify the direction of magnetic force? Through your palm. Okay. Another concept that we have to know in identifying the direction of the magnetic force is these two illustrations on your screen. So we have A and letter C. This will give us the idea on the movement of the charged particle or proton, for example. The circle with dot or in letter A indicates that the direction of the magnetic field moves toward us. Okay? The direction of the magnetic field or your fingers move or points toward us. Okay? While the dot with X or plus sign indicates that the magnetic field moves away from us, or the direction of the magnetic field or your fingers is on the screen. Okay? The direction is on the screen or to the paper. Now for letter A, let's try example letter A. The direction of the velocity is downward, south. South siya. The velocity is downward, and since we have circle with dot inside, meaning the magnetic field is pointing toward us. So basically, the direction of the magnetic force is moving to the left. Okay, it's moving to the left. That is the direction of the magnetic force, since the palm is pointing to the x-axis. Okay, x-axis. Now, sa letter C, uh, since we have that with x, or meaning the magnetic field is moving away from us, or so the direction of our fingers, we should point our fingers toward the screen or toward the paper, and the direction of velocity is going to the right. Okay, going to the right. So meaning the direction of the magnetic force is upward or on the positive y-axis. Okay, the direction the direction of your palm, okay, is toward upward, okay, upward or toward uh, positive y-axis. Okay, that ends my presentation this evening. I hope you learned something from my presentation. Thank you, everyone.